Okay. So, hunting for maxima and minima. So I actually, we have a theorem that says if you have a continuous function on a compact set, you're guaranteed that it has both a local both a global maximum and a global minimum. So I want to actually introduce a little bit of terminology. What do we mean if you have a function on a domain in Rn, and I'm not saying anything particular about the domain at the moment, it's real valued. What does it mean to say a point in that domain is a maximum point, minimum point, local maximum point, and local minimum point? So let's say f has a local, let's just say, put it in pieces, local maximum or minimum at the point A in your domain if what's true?
All the points around it are...
Don't even mention a derivative to me.
If all the points around it are less than it, it's a maximum. And if all the points around it are larger than it, it's a minimum.
Now, how are points?
Well,
there's a
value.
The values, okay. So local is going to mean that there is some neighborhood of A. So there's some positive delta, so that if you look in the ball of radius delta around A, what Dan is saying is for it to be a minimum, oh yeah, and in domain X, right? So you're in the ball centered at A and you're still in the domain. Then minimum, or maximum should mean that nearby the function is at worst that high, but usually that high and lower, right? So for all x in near A in the domain, f of x is respectively less than or equal to f of A in the case of a maximum, and greater than or equal to f of A in the case of a minimum. Everybody agree with that? So this would be at the point A here, and I'm thinking of graphing the function nearby, then that would be a local maximum, and a local minimum you would look. But you're not specifically requiring that it be strictly bigger or strictly less. So if you want to blow your mind a little bit here, suppose you look at the function that's 1 when, let's just do this in R, when x is rational, and 0 when x is irrational. You have a graph in your head for that? So at all the rational points, the function's up there, and at all the other points, it's down here. Notice I was very careful. There's a dot if and only if there's not a dot there. Sure. All right, so what about, what can you tell me about local maximum and local minimum points?
All points are local
All,
We got a whole bunch of maximums and minimums. Nothing in between.
All rational numbers are local maximum points.
Oh, yeah.
Would they be
And
minimum
all
as well?
irrationals, local minimum.
Minimum.
Weird, isn't it?
Not cool.
Every A in, I'm so used to writing vector symbols. Every A in Q is a local maximum point, and every every A not in Q is a local minimum point. Perhaps slightly more interesting if you took a trough where this was all at a certain height. So maybe I should draw it slightly better than that. No, I didn't draw it very better. Well, you get the idea. All these points on the low end of the trough are local min points. Even though there's a whole line of them, they're all lower than everybody nearby, or equal to in height. Okay. So we say F has a global. So you guys, what word did you use for that in your beginning calculus class? Absolute? Absolute max, absolute min? I don't like absolute just because you start getting confused with absolute value. So I prefer to say global. What does it mean? It just means so what changes?
You just get rid of the ball, essentially.
Get rid of the ball.
Yeah.
If for all x in the domain, this is true.
So it's still less than or equal to.
Yeah. But now, for all x in the domain. Now, suppose f happened to be differentiable at a point. How would you detect that it might be a local max or a local min?
Since the derivative is 0. Yeah.
Well, it's an f to our function.
So true or false? If A is a local max or a local min and the function is differentiable to A, then the derivative of f at A is 0.
True.
True.
Yeah, no,
This seems, no, because it could just be a
does not
straight
exist.
line.
No, but assuming it's
If
differential.
it's just a line.
then yeah.
It's just a line.
True.
What if it's on the end?
Yeah.
True or false?
True.
If the derivative, if f is differentiable to A and the derivative is 0 at A, then A is a local max or a local min.
No. False.
That's what you were thinking of. Now what about a function on an interval that goes like that? This is a maximum point, this is a minimum point.
But it's not differential.
Sure it is.
Differentiable there, but the
That looks
derivative
pretty
is
different to me.
But he's you know how to do calculus.
Sort of.
So if we're in Rn, we had better make sure that we say local minimum and you're at an interior point of your domain.
But that wouldn't meet your criteria that its slope is 0.
That's exactly my point.
You gave us the criteria. You said, and the slope is 0. The derivative is 0, yeah.
Do you think about a different case?
Okay.
What? I'm sorry.
I'm sorry.
I'm done.
So suppose well, okay, you're on my second statement, not my first one. That's why I was back on the first statement.
Oh, okay.
Right? Assuming it's differentiable and you're at a local max,
Right,
you
okay,
guys all
there you
told
go.
me it was true the derivative is 0,
That's false.
and that's false.
Okay, all right.
So suppose f is differentiable, I'm reiterating, at an interior point A of the domain. Okay, these are not interior points of the domain here. They're frontier points, right? And A is a local max or a local min. Some of you may wish to call that a local extreme point and not have to say max or min. I'm okay with that. Then the derivative of f is the zero linear map. So I'm warning you that you better not put yourself at a frontier point and expect the derivative to have to be zero. Okay?
Why do you have to say that like the derivative of matrix is the zero matrix when it's something to R?
Because it tells multiple variables.
Oh, okay.
What do you want me to say?
Oh, I
One
was
gradient?
No, it was just I was getting confused because I thought like I was assuming one variable, but then
Oh, no, I'm in n dimensions here.
yeah.
Okay, so this is supposed to be a matter of reviewing from your single variable calculus why you knew that if you were on an open interval around a point and you had a maximum at that point, say, that the slope had to be zero. This came up actually in some homework back in chapter 3, and some of you were actually trying to give a proof of this, and I said, no, you can just use it from single variable, but we'll review it, so here we are. Got count.
If the first graph that you drew on top had those 2 points not included, so it was like open, could you have a local max or
You
min?
would not have a max or a min
Okay.
if it were an open interval. So how do you know you have a differentiable function, what does it take to show that the derivative is zero at a point?
So that all the
At the interior point in the domain.
All the partials, right? The derivative matrix is the matrix of partial derivatives, so we need to see why the partial with respect to any variable at A vanishes for any I. So basically, you're back in a single variable situation, right? This is what I told you was one of the common themes in multivariable calculus is when possible, reduce yourself to a single variable situation. If I'm trying to do the derivative with respect to xi, I'm fixing all the other variables and varying just xi, and so the picture really is slicing through and looking at a curve that looks like what you did in single variable calculus. So you can think about a function of t, which is just f of putting in all the coordinates of A other than the ith one, putting a t in the ith coordinate, and then varying all the other, letting all the other coordinates be fixed. So if g of ai is greater than or equal to g of t for all t in a neighborhood, you're looking at a picture exactly like what I was saying. Here's the t-axis, here's ai, here's a function that's biggest or at most that height at ai, biggest at ai or at lesser height or at most that height nearby. Then how do we see what g prime of ai is? This is what the partial derivative of f with respect to xi is going to be. Well, I hate to remind you, but you have an intuitive way of understanding this from your beginning calculus class. Do you not? How did you understand this when you took calculus the first time? Why was the slope 0 at a max point?
Goes
It's
increasing.
increasing on one side and decreasing on the other.
It's changing sign.
What's,
The tangent line is flat. That's it.
okay, the slope, okay, so, or you could think about if the slope were not 0, if it were positive, what would go wrong?
If you went along the line, it was slightly
A little bit to the right, the function would tend to be higher. And if it were negative, a little bit to the left. But the easiest way to write this down and just nail it is to write down the limit definition. G at point plus h minus g at point over h. Limit as h goes to 0. Well, when h is positive, I have a positive number in the denominator. And what do I know about the numerator? What do I know if I move over here to ai plus h? What do I know about the function value there compared to the function value there?
Less.
Less or
Equal.
equal. So this is less than or equal to 0 divided by a positive, which is
Negative.
Negative.
less than or equal to 0. When h is less than 0, what happens?
Something.
Greater. Greater than or equal to 0.
Why?
Because it's decreasing.
The numerator is
increasing.
still
Less than or equal.
less than or equal to 0, and the denominator is now
Less than.
negative. Negative over negative,
Positive. Greater
it's
than or equal.
greater than or equal to 0. So this limit exists because the function's differentiable. From the right, it's negative or 0. From the left, it's positive or 0. Ergo,
Gotta
it
hit
must
zero
be
somewhere.
0. Okay. So all the partials have to be 0.
It's
So we'd like a word for functions that are differentiable that have a point where all the derivatives are 0, all the partials are 0. If f is differentiable at A, and the derivative matrix is the 0 matrix, or the gradient vector is 0, either way you prefer to think of it, we call A critical.
Oh, yeah.
Now, I'm saying this because some of you had calculus books for single variable calculus that also included other points as critical points. I don't want to mess with that. So for us, critical point means exactly a point where the function is differentiable and the derivative is 0. So if you're at a frontier point, you're at a point where it's not differentiable, not talking about a critical point. All right, so now I get back to the question I was raising earlier. So what we proved is, if the function is differentiable and you have a local max, local min, it must be at a critical point, if it's an interior point. Must a critical point be a local max or a local min?
No.
So this was the question I raised earlier.
It could be a point of inflection.
So what's your standard example from single variable calculus? Which has a
Critical point.
critical point at 0, which happens to be
Point of inflection.
a point that is neither a max nor a min because the function is always increasing. And yet there's a critical point. Okay. Now you could sort of dismiss this as being a fault of having a very high exponent here. I mean, really you don't like exponents bigger than 2, do you?
Sure. My favorite exponent is x to the 4th.
Is 4 really your favorite exponent?
Absolutely.
Okay, I'll remind you of that in a while.
Raised to the 4th both sides.
Is there any way you could have rigged this with one variable without having a higher exponent than 2?
Wait,
That's,
what?
that's just,
I don't understand.
no, that's too much, that's cheap. How about that?
X squared
Well-
and x what?
I mean, presumably, if you had a quadratic of any form and you had a critical point, it would be a max or a min. Is that true in multivariable? If I rule out exponents bigger than 2, do you think it's always going to look like this or this, hopefully?
No.
Yes. I wish it would look like that.
I didn't ask what you wished. I asked, do you think that if you took a graph of a quadratic polynomial, that it would have to look like one of those if you were at a critical point?
Wait, just the partial in one direction?
With one variable?
No, so 2 variables.
Oh, no.
So what I'm asking
Saddle
is,
point.
Yeah.
can you give me an example mapping R2 to R where your answer to this is still no?
The saddle.
Saddle. So this is Dan's favorite is apparently x to the 4th, but my favorite is the saddle surface.
Single variable.
Or actually, I prefer to draw it with the minus in the front.
Why?
So you will recall that we talked about this. We said this function, the graph of this function, is upwards pointing parabolas in the y direction, because you have y squared. The downward pointing parabolas in the x direction, because you have negative x squared. And so you had a downward pointing parabola cross section there. And you'll recall that those downward pointing parabolas move along with their vertices along this parabola. And as you shift for fixed x's, you still see parabolas that are pointing upward. So at the origin, in fact, both partials are 0. The tangent plane at the origin is flat. But it's certainly not a max or a min. Why?
Because in one
Because it's either
direction
going
it's
up
in
either.
mid and in the other it's in
So definition, so 0 is a critical point. As you can check, both partials are 0 at the origin, but is not, clearly not, a local max or a local min. So definition. And I'm warning you, the author of the book screwed up. So if you're going to look at the book, there's a big typo here. Look at the errata sheet and fix it. If F maps X to R, X and Rn, A is called a saddle point, a critical point, so differentiable at A, and derivative is 0. So it's a critical point. Okay, so this is all preamble here. A critical point, A, is called a saddle point if what?
It's got its worth in calculus.
I don't want to talk about second derivatives.
That comes next week.
So, we got the saddle
One of the
surface.
It looks like a saddle. Okay, well, what But what does it mean that it looks like a saddle? Well, it means that if you look near your critical point, no matter how small a ball you take, around your critical point in the domain, you see points where the function is both above and below. So it's called a saddle point if for every ball, think small ball centered at A, there are points x and y in the ball centered at A where f of x is less than f of A and f of y is bigger than f of A. So arbitrarily close to A, there are points both above and below the height of f of A. What I believe the stupid author screwed up was requiring that this be true for every delta. If you don't require it for every delta and you just allow it to be true for some huge delta, then anything that looked like this, any function that had a saddle point, say here, and then went up and got tall here, well then you would decide that that was a saddle point.
Couldn't you say that, like, by that definition, you said that any point was a saddle point?
Any critical point, you mean?
No, any point at all, like, just.
Well, no, but I said a critical point.
Okay.
Unless you see this definition of critical point.
So the A here in your domain here is in fact a local max. It's a critical point. But if you took a huge ball around A, you'd see points where the function was bigger. Well, I don't want to call that a saddle point. You have to, it has to be locally. As you get close to A, you have to see points both above and below.
Should we also do the thing where we intersected x with the ball? Or is that not necessary this time? Because you have that in the
Yeah, I have to confess here that when I'm talking about critical points as being points where the derivative being 0, I'm thinking of interior points. So
Okay.
I'm working in an open set actually here. So I wasn't, this x should have probably been an open set now.
Okay.
Thank you for catching that error. Question? So the videographer will recall my liking to pose this question. Single variable calculus, true, false?
False.
True, false? Function
either right answer
differentiable
anyways.
everywhere on R has a single critical point. F has exactly one critical point. A, which is a local minimum. Statement, then it must be a global minimum.
True.
No.
False.
False.
Found on all of R, differentiable everywhere, no screwed up behavior. Here's your point A, and it's got a local min there. It's the only critical point.
No.
No, because it could like,
Yeah, I can like, yeah.
down and
It's
then-
x, I don't know what it looks like.
it could look like a leafy M.
Yeah,
right
yeah,
back
they
down.
don't have
They don't have
We
more
don't
critical
have other
points.
critical
Yeah, like
points.
Oh, that's shit.
Oh,
Never
exactly
mind.
one critical point, I thought it was
Yeah.
one local, right?
True? Well, what about this?
He's trying to trick us.
So Philip, what are you thinking of?
That's pretty too, yeah. We
It's a
have
trick, so it's definitely false.
So what would it mean if it were not a global minimum point?
That
There's some
there's
point
a point
lower
in
than-
F lower than that.
There is a point where the function value is lower. Precisely. Okay, here it is. Lower value here.
How do you get there?
How did you get there, Mallory asks.
'Cause you have to be increasing between A and B.
Yeah, so it's not, it's differentiable everywhere.
It's differentiable everywhere.
So if you wanna get
Why
down,
must the derivative have to be 0 somewhere else?
Because it would have to decrease again.
That's where it needs to change signs.
So can you start quoting me some theorems from calculus that might be helpful here?
The intervals that mean values.
Yeah.
Rolle's theorem.
Rolle's theorem. How do I do Rolle's theorem?
Yeah, didn't he invent?
Rolle's theorem says if I have 2 points
Butter on?
at the same height, then there has to be a place where I have a critical point in
Right.
between them.
Yep.
How do I find 2 points at the same height?
You find the point in between A and B where the height is equal to
Why is that?
A. Because mean value.
The function's continuous, and it's,
Yeah.
so it's going up a little bit here, presumably then it has to go
Yeah.
back down. By the intermediate value theorem,
And
it had to cross this value there somewhere,
Yeah.
and so by Rolle's theorem, you had to have a maximum point. Or you could have just argued by the maximum value theorem somehow on some closed interval here, that there would have to be a max. So I think there has to be another critical point, agreed?
Yeah.
So what do you vote?
true.
True.
I mean, let's just say.
Okay. You guys are acing this test so far. F differentiable everywhere. F maps Rn to R, and bigger than or equal to 2.
Okay.
If Dan wants, he can make n be 4, but I doubt he wants that. True, false. Suppose F has exactly one critical point. A, now it gets a vector sign, which is a local minimum. And A must be a global minimum.
False.
Whoa, 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 what?
It's not a local minimum.
Settle point is the critical point,
It's not,
but which is a local minimum.
So I have an A, and again I have this picture here. Question is, must it be a local minimum?
Well, it have to have some way
It must be a global minimum.
Has to be able to decrease while it's not equal. It's kind of.
Could it curve some way that so that some of the parcels are 0, but not all of them?
That's what I'm thinking. He just said it more.
Yeah.
So, okay, so again, suppose it weren't, then there'd be some point B in the domain where the function went lower than there. So it went down here somewhere. What are you envisaging happen?
There would have to be like
Some slanty slope thing going on.
So I think what,
there would have to be a cross
That's
section.
slanty slope.
Like I don't know how to
so what happens if you try to make it be like the one-dimensional picture and you walk from A to B?
it has to be just like
It has to do this, doesn't it?
yeah.
As you walk on this path, you have to go up and then come back down somewhere.
Yes.
Have we answered the question?
No.
Why?
Because
We don't know.
Because that might not be
Plane
flat,
also
right? It could be
There's no Rolle's theorem.
Well, no, I still have Rolle's theorem on this
on that
one-dimensional
one, but
slice.
not necessarily on the
So
other
just
one.
take-
This
Oh, okay.
one-dimensional slice does have a high point.
Right.
But
Just
we gotta-
take parabolas.
We got a
Like,
slanty
not
slope.
all of them.
No, parabolas would give you a 0 though. They'd give you a maximum if you have parabolas. You'd have to have like some sort of just
Where
line.
would it give you a maximum?
If you had parabolas going
Up.
up, if you had parabolas going. No, it would still be a critical point, but it would.
Oh.
It's exactly one critical point though.
Oh yeah, so I mean, I agree that a global paraboloid is an example where this is true.
No, I meant if you take parabolas like sprouting out for that thing. Like
Yeah.
It just like they're all going up, so there's no global like it keeps.
Yeah.
But then you would have
But you-
more than one critical point.
Where would the other critical point?
No, no,
Because
no,
it would
no,
be-
but
A
Wait,
parabola
how am
going
I
down.
taking your paraboloid shape and having a point where it's lower?
I'm sorry, not
Oh,
not a parabola, but
no,
like when you
I know what
do
you're saying.
when you had up there, you had like one hyperbola, and then you had hyperbolas like branching off of it. Like I don't know how to explain that very well. Like if you had parabolas, if every point on that like figure that you've drawn,
So at that.
not
like
the
the
other one,
saddle
that one.
surface.
Yeah, there's a parabola where the minimum
We'll just
is.
draw a parabola.
That'd be a
Is-
parabola.
Draw a
So-
plot.
Would be a maximum.
So are you arguing that it,
have an extra critical
Are you arguing that it has to be
so
a
are you trying to
There.
create a surface where this is false?
Yeah.
Okay. Now, I mean, the obvious things that people could do is to take a goal and make it out of putty and bend it over. But then you have a whole circle of critical points.
So you have to somehow get a slant.
So, all right, so this is my challenge to you guys.
No,
Either
but it would.
find me a function, or make me a paper mache model or a clay model or something, which demonstrates a function. So you guys are voting what?
False.
False. So I want you to find me one. I don't need formulas, although if you want to make up formulas, I'll live with it. But I want you to make a convincing shape or describe it in some other convincing way where it's clear that you don't have any other critical points besides that. Okay.
But it can only have one critical point, right?
All I want is the one low point here that's a local min,
Right.
but I want the function to go lower
Right,
elsewhere without having any more critical points. And I want it defined
Right.
on all of R2.
Oh.
I'm
That's
voting.
So that's my mini challenge for you guys.
Well, you could just.
Does n have to be greater than equal to 2? Oh, equal to, never mind.
2, yeah, n equals 2 is fine.
You can cheat a little.
I can't begin to visualize graphs of functions in 5 variables, so
You can-
I'm not expecting you to.
You can kind of define it just to be flat everywhere it has the.
No, flat,
Or just like
critical
one or
points.
whatever, and then just have it come in and be differentiable.
But Dan, I want to emphasize what Dan was saying here, that yes, on this one slice in this one direction, we did have a flat direction, but that didn't mean that it had to have a flat tangent plane. As long as in some other direction at this point you're headed uphill
Right.
or downhill, you won't have a critical point there, even though you have one direction where the directional derivative is 0. Okay, so I'll let you ponder that challenge, and I want to just do something sort of easy for the end of class today. So let's consider the following function. F of xy equals x squared minus 3x squared y plus y cubed. And by the way, I could have given you web work to do, but since I'm just getting to this now, I didn't. It will be on next week's assignment where you have to find critical points of lots of functions and just practice some algebra, and then you're going to have to tell me if they're maxes or mins or saddle points. So we'll learn that next week. So suppose we're on the domain where x and y are both between -1 and 1, and I want you to find me the maximum and the minimum of this function.
Okay. So we got
Is this smooth, nicely differentiable as many times as we want,
Yeah,
continuous?
yeah.
So we're guaranteed
a
max min on a compact set.
Right.
So we're guaranteed max and min on the compact X.
Oh shoot.
Go forth and find them.
We know
Yes, and check.
that x squared values are always going to be.
Are you squaring both sides again?
No, I'm not. Not remotely. No, because x squared is always going to be
X squared
less
equals
than.
Find the
Why
point
don't
where the
you go
derivative
find
is
out
0.
the actual, like,
Yeah, why don't we find the derivative, guys?
I don't like that idea.
So what's the derivative? And again, if you prefer to write gradients here, and rather than writing a matrix as a row, I just write gradient equals, I don't care. All right, what's the x partial?
2x
2x
minus
minus
3x.
6y.
6 x y.
What's the y partial?
Negative 3x squared plus 3y squared.
Find me where both partials are 0.
The origin.
That's fine.
Just another.
I bet there's some other point.
Factor out the 2x.
Now, let me warn you that although I've trained you to do lots of stuff with linear algebra and matrices to solve equations, you can't use matrices to solve equations here because
They're not linear.
not linear.
Okay, which is
Okay.
y equal 1/3,
So
y
what should-
equals 1/3.
So first of all, we should divide by 3. And we should say y squared equals x squared, right?
Sure.
And the first equation, we should do what? Divide by?
Divide and factor.
X,
Don't divide by x or you throw away roots.
2.
Do not divide by things other than constants or you're squandering roots. So what should I do? I should factor
You could factor 2x.
2x, but I'm going to get rid of the 2.
Oh, okay.
Since 2 can't be 0 in our world in this class.
If we already know that like y equals 0, x equals 0 is a point, then why can we factor out x?
Because there might be x equals 0 and y equals something else. I don't want to
Okay.
lose any possible roots.
Okay.
So what have I got? X factored out, 1 minus
minus
3y. It turns out, I don't think that's going to happen, but it might. Did I do this correctly?
Beats me.
So now how do I solve these equations? Well, either x is 0,
Or
in which case,
Y
y
is
is
0.
0.
or
Y
y
is
is
1/3.
And
And x could be plus or minus 1/3.
Does everybody agree with that? Because of this equation, x could be either a third or negative a third.
Yep.
So I found me how many critical points?
3. Well, other than the one we already found 2.
So I've got 0, 0,
1/3.
1/3, 1/3, and negative 1/3, 1/3. How do I decide where the maximum is and where the minimum is?
Plug it back into the function.
Plug in back to the function.
So one of them is 0.
Yeah, I can do the hard one. I did the hard one. F at the origin is 0. I did the hard
I
one.
did it first. Well, the
Now
third one
notice
is kind of like.
that it has only even powers of x. So the values at these 2 points are going to be the same. So I'm just going to shortcut and say at f at either of those points is
We got a
One
9,
ninth.
1/9, and then another 9.
No.
1/9 minus 9 plus 1/27.
1/9.
I believe Daniel is correct.
Yeah.
That's a first.
Maybe not at first.
Second.
So what do you tell me the answer to the question is?
No, wait. We gotta do the corners.
Oh, rats. So we found in our domain
I wish I could put that
3 critical points, and I was going to let you go home 5 minutes early. But Dan said, no, wait.
Thanks.
Yeah, that's safe.
Ah, I like it. Or
So
don't.
what have we forgotten?
Endpoint points.
Well,
X
wait.
Well, the front.
The
Frontier.
Yeah.
Yeah, we only know that if you're at an interior point that's a max or a min, it must be one of these 3 points. But as often happened when you did single variable calculus problems and you had closed intervals, you had to check
The frontier points.
the frontier points or the end points because they could often be maxes or
That's
mins,
why we used to call
but were
them
not
critical
critical points. So how do we check, quote unquote, frontier points now?
You just plug them in and see if they're.
Wait, what do you mean plug them in? There'd be a lot of points to plug in.
Do you have to like parameterize the order as a function and then?
It's easier in this case, but yeah, what Cal's saying, in general, for example, if I were on a disk, on a ball, and you wanted to know what's happening on the circle, probably be easier to parameterize it and make it a single variable calculus problem.
So it's what, like.
But in
y.
our case, we have 4 line segments, and clearly, I'm saying clearly, but I want you to tell me why it is in fact clear, that on this line segment, the function behaves exactly as it does on this line segment.
Even.
Because of the x squared. So on these two pieces, I'm going to fix x equal to 1, and I'm going to look at the function of y. X is plus or minus 1. I get 1 minus 3y plus y cubed, and y is varying from what to what?
Negative 1 to 1.
And on the other pieces,
It's not so.
on this piece, I would have
Y is 1.
Y is equal to 1
h of x
is y, yes.
X1.
X squared
Minus
minus
3x
3x
squared.
squared plus 1.
and on the bottom piece, I'm running out of room.
You
X
get
squared
4x
plus 3x.
squared minus 1.
On the bottom piece, I would have a function of x, which is,
4x squared
4x
minus 1.
that becomes a plus, right?
Right, exactly.
4x.
And that's a minus.
And that's a minus.
So it's 4x squared minus 1.
You can factor that.
All right, so
That's fun.
It's 2x.
how do we find the, and on these two, x is between negative 1 and 1. So how do we decide maxes and mins for those single variable problems?
Check the derivative.
And,
And the frontier.
and,
The frontier.
And then
and,
look
The
at
frontier,
the
but like the
corners.
edge.
we have to check endpoints.
Wow.
So does it ever end?
Right, it has ended, right? So,
And then
It's x squared plus 3x squared.
did I make a mistake?
No.
Because you're looking at where y is.
All right, so let's just quickly finish that up. For the function g,
No, it's back to thing that one.
critical points are at,
Tail line minus, no, 3 minus 5.
well, it actually ended up at the endpoints. How convenient. So you would plug in
1.
1 and negative 1. G of 1 is negative 1. G of negative 1 is 3.
Uh-oh.
What do you mean, uh-oh?
That just means they're bigger than that.
Yeah, I mean, yeah. So your eyes in that face are not max points.
Just erase them. Erase its old face.
wait.
What about
It's
h?
so local.
Oh,
We don't like
H prime of 0, h prime of x,
Minus 4x.
huh?
Negative 4x.
What are the roots, what are the critical points of both of these?
X equals 0.
I'm so confused.
So at 0, we have 1, and at 0 for j, we have
Negative 1.
negative 1.
Wait. Yes.
But I have to look at endpoints.
Yeah. Endpoints are crucial.
Well, wait a minute, I've already got those endpoints. Because they were showing up as the
Oh, that's so good.
endpoints of those intervals, so I don't have to do these endpoints because they've already appeared there. So we already did that, right?
That's a critical strategy for you.
So at this point, we've got 1 here, we've got negative 1 here, and at these other endpoints, they're negative 1 and 3. So at the round point it was 0, and at these it was 1/27. So So what's the upshot? What's the maximum?
3.
And what's the minimum?
-1.
Just as I suspected.
You don't
So, in fact, it's all very disappointing because the critical points in the interior were totally worthless.
Yeah.
That's generally how it is.
All right. Have a good weekend if I don't see you in office hours.